So we were talking about compounds. Compounds is two or more different elements that are stuck together by a chemical bond. And we're going to pick up where we left off with the chemical bonds. I could say I'm going to take atom A joined to atom B. That's not boron. That's just some generic atom. Okay. And this dash right here, actually we're going to be talking about how do you show them arranged and everything, but kind of think of those as basically two electrons, a pair of electrons that are sticking them together. And in my convention, if you see a solid dash, basically that means that electrons are being shared. Two electrons shared. They have joint possession between those two atoms. Okay? And we call that a covalent bond. Covalent bond. And actually, I kind of had two things up here. I had covalent or molecular compounds, and I had ionic compounds. Kind of that's where the word covalent is kind of associated with that. And then if I have an A, if I go like that with dashes connecting those two things, that actually means electrons have been transferred. Okay? And we're going to see that in today's lecture, it's the metals. I'll kind of put the metals on the right for some reason. Excuse me, metals on the left for some reason. I guess because they're on the left of the periodic table. Okay, and the non-metals over here on the right. Okay, they're going to the right. And what they see is kind of stepwise, and I picked on sodium chloride. Basically, an electron or two or three is transferred. Okay. An electron is transferred, and we'll talk about why that would be. But as an electron is transferred, most people are cool with this. So the one who gets the extra electron becomes negatively charged. So I'll put like a little negative superscript up there for the B. And now the metal actually is deficient in electrons and it becomes positively charged. So then all of this is to say that, and there's a slide to kind of say what it is, but anything that's positively charged is a cation, and anything that's negatively charged is an anion. Not to be confused with an onion, I know. So that's all it is. That's totally all it is. So kind of in the backdrop of that idea, whether electrons are shared to form a covalent bond or electrons are transferred to form a cation and anion, is this idea of electronegativity. So Linus Pauling, I don't know what year it was, actually came up with electronegativity values for each element. An electronegativity value assumes that that atom is going to be connected to another atom, and I like to think of electronegativity as like a tug of war for the electrons. Electronegativity is the tug of war for electrons. The symbol for electronegativity is the Greek letter chi, so it's just kind of a fancy X. That's electronegativity. Bless you. So you have a pair of atoms, atom A and atom B, and electrons are either going to be shared, electrons are going to be transferred, and it has to do then with kind of looking at the nature of the electronegativity of those two atoms that are bonded together. And I've got some images or figures to show you with regard to electronegativity, but this is my favorite one coming up. This actually, you recognize the periodic table. And this actually has, in each of the boxes, has a Pauling value for electronegativity. So you can pick an atom, put them together, and kind of see what's going on with regard to electronegativity, those pair of atoms that are stuck together. Okay, are we ready? Oh, there was something up there. So I'm going to go ahead and this is something new for me this semester, but I think your textbook does this. I'm going to do an M for metals, okay, and I'm going to just do an X for nonmetals. M for metals, X for nonmetals. And as it turns out, the metals have low electronegativities. I'll use the symbol. Metals have low electronegativities, low chi. Okay, and nonmetals have high chi. Greek letter chi. They have high electronegativity values. So that means in this tug of war, okay, that actually these guys are going to want to, what we say, hoard electrons. Okay, in the tug of war, literally, it's like they're going to hoard electrons. They're going to hoard electrons to the point where electrons are transferred, actually. And these guys over here, the metals tend to want to give up electrons. Good for them. It's a nice situation. So electronegativity, if you're dealing within the period, within the row, electronegativity increases from left to right. And that's what, this would tell you. And electronegativity increases across the row. And electronegativity within the same group increases from the bottom up. Okay? So I usually kind of think of it, and you'll see my hands do this, as basically it increases this way and it increases this way. So you'll see me kind of like this and like this. Okay, so the highest electronegativity is like right over here. So I have 3 figures to kind of show you electronegativity values. In this one, the higher the column, the higher the electronegativity. Oh, by the way, that trend, electronegativity increasing this way and increasing this way, that is limited, again, just to the group A elements. Okay, so we're kind of throwing out the transitions. And here, this one actually includes the B elements, the transition elements. We kind of see some kind of ups and downs. But if you just focus on the 1A, 2A, and the 3A through 8A. Now check out 8A, right? We're going to be talking about them. 8A, of course, is your rare gases, noble gases, inert gases. 8A doesn't want to actually connect to anything, so there's no tug of war to be had. Okay. And this is the one I printed out right here, electronegativity values. I think you have this maybe in your textbook, maybe not, but hopefully you can read it if you need these values. I think he won a Nobel Prize in chemistry for that. So this whole tug of war thing, I think it works pretty good. If you have a big difference between the electronegativity values of the 2 atoms you're connecting, hey, that took over your spot. If you have a big difference, then actually think of, if you watch tug of war, basically one side wins. Okay, and it's going to be the non-metal that wins. So an electron will entirely be transferred. And if an electron is transferred, then we have a dot, dot, dot. In my sense, that dot, dot, dot chemical bond is an ionic chemical bond between a cation and an anion. Okay. If you take a pair of atoms to be bonded together, to be bonded together in a chemical bond, and actually the tug of war is moderate, okay, then electrons are going to be shared. Now, they may not be shared equally, and actually there's a way to handle that, and that's an actually important player in atoms that are covalently bonded together. And I'm going to give you some values here in a minute of at what point does an electron jump ship from a metal to a non-metal? What's that kind of threshold? Okay, but usually if you pick 2 non-metals, now remember what we talked about, non-metals are these guys over here on the right. Non-metals are by far the fewest elements on the periodic table. You pick 2 of them and you're to go ahead and see what the electronegativity difference is, okay, then we're going to see that electrons are shared. The bottom one says if you pick a metal and a non-metal and you do an electronegativity difference check, you're going to see that the non-metal actually has high enough electronegativity. Hoard for electrons. Electrons going to be transferred to the non-metal from the metal. So, let me see, do I want to add this? Do we want to add this to our, pair or molecular compounds and ionic compounds? I actually think it's already there. If you made the list that I made on the board, one of the things you guys had was that over there on the right for ionic compounds, you said contains a metal. This is exactly what this is saying. Contains a metal. Yep. And then you had there on the left for molecular compounds or covalent compounds, you had all nonmetals, and that's exactly what that is. So we're kind of just being consistent with what we already kind of talked about. But now this is why, okay? When you have a pair of nonmetals, their electronegativity difference is small enough that electrons are going to be shared, not transferred. All right. So in physical science, we have the Greek letter chi for electronegativity, but we use the Greek letter delta, which is a triangle, for change in or difference. I don't know if I've run into that before. So that is the Greek letter delta, lowercase, I think. Okay. And delta always means change in or difference. So the difference, you're probably familiar, you're going to subtract. And that's exactly what we're going to do here. The thing we're going to subtract are these values, the Pauling values. So basically, if you have atom A and atom B joined together, you can come up with their delta chi, the electronegativity difference. How? You just look them up and do a subtraction. So if you do a subtraction, if you do a difference, and you find that your nonmetal is at least 1.7 Pauling values higher or greater, okay, than your metal, then an electron's going to be transferred. And what does that give you? An ionic bond. Anything kind of less than 1.7, and actually you have what we call a covalent bond. So 1.7 is kind of the snapping point. But leading up to 1.7, electrons are shared, but they're not shared equally. Let's see, let me do an example. We have a lot of carbon and oxygen bonded together, and you have to kind of look, you have to isolate each pair of atoms at a time to understand the nature of the chemical bond. So let's pick on carbon and oxygen right quick. So what if I have a carbon that is bonded to an oxygen, and somebody says, well, okay, what is the electronegativity difference? What's the delta chi? So one of the things right off the bat, do you see where we can find carbon on the periodic table, and we can find oxygen on the periodic table? How many people think carbon, we said it, electronegativity increases across the period from left to right. How many people think carbon has a higher electronegativity value? That's right. Oxygen has the higher electronegativity value. Exactly. So I'm going to go ahead and use this, and I'm going to, you actually have this in your notes. So I'm going to pick 3.5. Okay, and for oxygen, and I'm going to pick 2.5 for carbon. Now those numbers in green are the electronegativity values. Okay, we good with that?
Will we ever have to find those, or will we always be given those?
I will always give those to you in this class. Yep. One thing about it I didn't mention, but it's, do you see where, do you guys know what those lines mean in math? Absolute value, exactly. The way I get around absolute value is I always just put the bigger one first if I'm doing a difference. So, so we could come up with the delta chi, okay, is the absolute value of, I'm going to put 3.5 minus 2.5. Does that work for you? Okay. So I got 1.0. So here is kind of the situation of this bond right here, okay, polar. Now, if somebody's kind of polarizes a room, that means they kind of come in and basically everybody takes sides, okay? And that's kind of what we mean by a polar bond. In this case, though, we mean electrons are scooted to one or the other, and you told me that oxygen is a higher electronegativity, so guess what? Electrons are going to scoot over there. And we show that scoot by this. We use the other delta, no, partial, I don't know my Greek letters, but anyway, we do this. It looks like an S, and that means partial. Or in this case, partially. I don't know why we do this in, it's like a, sigma, delta. I don't know. I think it's delta too. Okay, so we go partially negative. Why? Because it's got the higher electronegativity value. And then guess what we do over here? Partially, what do you think? Positive, exactly. So with that partial negative and that partial positive, we had showed the polarity of that particular bond between those two atoms. And to me, you kind of have to look at it almost a pair of atoms at a time to understand kind of where, and it's literally, we've talked about electron clouds, literally the electron cloud will kind of those two electrons that connect those two atoms, will kind of be shown over to the oxygen.
So when do we know to do the partial and the non-partial? Like if it's a full negative and a full positive or partial?
If this would have been 1.7 or greater, then it would have been transferred.
Okay.
Yep. Okay, so I've got kind of some other, I guess I don't really have the compounds, but you see up here that it's switched around, but I told you the electron cloud is going to literally reside more over the atom that's more electronegative, which was oxygen in our case. So that kind of swelling gold thing over there, that's your oxygen. And the blue thing is your carbon. And then kind of back to what JC said, if you reach 1.7, and here they're showing two, I should have mentioned, the 1.7, what's the cutoff for electron being transferred? Depends on who you talk to and what kind of mood they're in. I kind of tease, right? So 1.7 is just ballpark. They've got it 2 for electrons may be transferred. But I hope the whole HCl thing works for you. If I find hydrogen on here, it has a Pauling value of 2.1. Let's just do that one right quick. I'll put the chi values. This is 2.1. Chlorine is, looks like 3.0. So what is delta chi? Yep, 0.9. Are electrons transferred? Partially, exactly. Like no electrons transferred. So this guy over here, the chlorine, is partially negative. The hydrogen is partially positive. And we talked about how the electron cloud actually is what gives the atom volume. So dang it, if chlorine's going to hoard electrons, then it's actually going to be larger. So that's all consistent. Okay. So again, this in italics kind of goes back to what we listed on the board when we talked about 2 types of compounds. We have molecular compounds or ionic compounds. Okay, and I said look for the metal, and actually on your next test I'm going to give you some just I don't know, maybe 5 formulas, and I'm going to ask you, is it ionic or is it covalent? Okay, and ionic, there's a metal. Covalent compounds, no metal. Okay, and what is hydrogen? Do you remember? For purposes of looking at the formula, it's a non-metal. Very good. Hydrogen's a non-metal for purposes of just evaluating your compound in this class right now. Okay, so these will be due on Friday. Let's take a look. They look like this. See, you can see like 46, you're going to get some, like, if you want to put exam on that, you can, because 46 is going to be on your test. It won't be those, okay? But the hint I've been saying is, and if you like, if you're a musician, sometimes if you want to mark up your, like if you're in rehearsal and you want to remember something, remember to look at the conductor. These are actually spectacles. That's my spectacles. That's what yeah, glasses, exactly. So anyway, it says look for the metal. And I'll go ahead and expand on that. Metal is equal to what? Ionic or covalent? Or ionic? Ionic, exactly. If there's a metal, it's an ionic compound. And my abbreviation for compound is CPD. All right. Then for these, it's kind of an interesting thing. What your author's done is A, B, C, and D. Your choices are, is it represent single atoms? Does it represent a molecule? Or does it represent a formula unit? So actually, 50 is actually related to 46 because, do you see I X'd out single atoms? None of those are single atoms, okay? Well, actually, I guess. Yeah, none of them are single atoms. B's not even a single atom.
There's two.
Right, exactly. So I'm like, really? You put that there? So your choices are, is it a molecular compound or is it an ionic compound? Because which one of these do you use for ionic compounds? Molecules or formula units? Formula units, yep. If you go back to kind of the the two types of compounds, we said if you have an ionic compound, you call the repeating unit a formula unit. That's it. Affectionately called FUs. I'm sorry, but it really is. Formula units, right? Okay. So they're actually 46 and 50 are related. So 78 says you're supposed to refer to, I believe, this figure, and you're supposed to say what is the electronegativity of fluorine, carbon, and sulfur. So you can do that, right?
Is that pretty much the same thing as what we have in our...
Yes, yep. Yeah, this should be the same as this one that I've been using. So for 80, you've got, what, 5 elements, and you're supposed to list them in order of increasing electronegativity. I would suggest that you can actually use figure 10.2 to check yourselves, but just use the general trend. Find them on the periodic table and know that it increases from left to right, increases from the bottom up. And you should be able to do that. For the last one are the delta chi's. The last one are electronegativity difference, exactly what we were doing just a minute ago, okay? So for A, you find electronegativity value of potassium, K, and you find the electronegativity of chlorine, Cl, and you take the absolute value of the difference. All right, and then it says, are you supposed to say, is that a pure covalent, polar covalent, or ionic? And I think if you look back, I'll go ahead and put it here. But pure covalent means delta chi electronegativity difference is 0. That's pure covalent. Polar covalent would be what? Between 0 and 1.7.
Oh, yeah,
Yep, 0 and 1.7. And then ionic would be what? Greater than 1.7. So yeah. All right. So on to the next part. Tomorrow it'll all work out well, but we're going to have to kind of do some learning in lab, which is fine. Let's see, I guess I'm going to kill that. So I already told you tomorrow the title of, I think it's 11. I think that like when you go to your lab manual, it's going to be experiment number 11. And tomorrow we're just going to solely focus on ionic compounds, so you should have a metal there somewhere, right? Okay. Now, 2 things I want to do in tomorrow's lab to get you ready for your test is you guys, by the end of tomorrow's lab, are going to be actually writing the formula for your ionic compounds, and you're also going to be naming your ionic compounds. So those 2 things, writing the formula and naming them. If this ever comes. No? Oh, good. All right. So in order to kind of put this in perspective, I like these first few slides because like, hey, we talked about that. And we did talk about that. Back in Unit 2, and actually that's a good point for me to kind of point out the obvious, that chemistry kind of builds on itself, so stuff we learned in earlier chapters and units we're still using. So we talked about how electrons are configured. Okay, and then we talked about the most kind of important electrons, the valence electrons. Okay, so I need to revisit that. Okay. The valence electrons are not necessarily the last added, but they are the outermost. They're what? The highest N, aren't they? Valence electrons. Well, you know we got to talk about electrons because we talk about electrons shared, electrons transferred. Okay, and the most important electrons are going to be the valence electrons. So let's just focus on, here's a, you guys probably don't have this in your notes, but you recognize the periodic table. Okay, we have the group A elements, 2 columns here, 6 columns here. Okay, 1A, 2A, and 3A. So 3A, of course, skips the B. So
We have this slide, we just don't have the periodic table.
okay, good. So here's 1A, 2A, and 3A. And we did talk about valence electrons. Do you guys remember, how do you know how many valence electrons an element has? It is a group number for the A's, exactly. So we have 1 valence electron for all those, 2 valence electrons, 3 valence electrons. Perfect. So hopefully fresh in your mind, again, from Unit 2, is this idea of the S-type subshell and the P-type subshell, how electrons are hanging out. Okay? So we actually talked about when we were coming up with electron configurations, we said if you come up with an NP6, where N is some number, 2, 3, 4, 5, 6, NP6, you have reached a rare gas. Okay? That actually is called, and I'll put the word up here. This, if we were to add up, and I think I mentioned it the other day, add 2 plus 6, you get 8. Yep. Sometimes that rare gas configuration is called a complete octet. And we're going to see that the reason sodium does what it does, the reason chlorine does what it does to form table salt, is because sodium wants to get a complete octet and chlorine wants to get a complete octet. Okay? So, and that animation doesn't play. Now, in tomorrow's lab, we'll be dealing with cation ions, positively charged, and anions, negatively charged. We're going to start out by dealing with cations and anions that just have 1 atom. They're called monoatomic ions. So I've kind of already talked a little bit about this morning. Cations, and the way I remember it these days is cat, like a plus with the letter T. Okay. And I think someone told me recently they remember anions like negative anions, negative anions, negative. Now with this whole getting a cation, it's something that's positively charged, and getting an anion, something that's negatively charged, remember the structure of an atom, the protons aren't going anywhere. They're set in stone, but the electrons can kind of come and go. That's what makes this whole thing work. Okay. So again, kind of like what we've been talking about this morning, how does that work? Well, how do we get our cations and our anions? Well, as it turns out, the metals are just, they have low electronegativities. They're like, yeah, dude, have my electron, okay? And the nonmetals have high electronegativities, okay? And high electronegativities, they hoard electrons and become negatively charged. So again, kind of like a deja vu. It's like we already did that, right? On your unit exam for Unit 2, we did a little bit of this where I give you the symbol of an element, and in the upper left-hand corner, I give you for that isotope the mass number, which is the number of protons plus the number of neutrons. In the lower left-hand corner is the atomic number of protons. That's optional. Now we need to talk about that whole charge up there. So if it's a cation, you're going to see a plus charge up there. And actually, you're going to see a number there. If there's no number, it's 1. It's implied 1. But if it said like +2, then it must have lost 2 electrons. If it's +3, it must have lost 3 electrons. Okay, and for the anions, you're going to see a negative. And if it's just negative nothing, that means -1. -2, it picked up 2 electrons. -3, it picked up 3 electrons, etc. So let's do this one right quick. Calcium. Ca is calcium. Calcium is atomic number 20. This particular isotopic form of calcium has a mass number of 39, excuse me, so kind of get your bearings. How many protons does it have? 20, exactly. Very good. Has it gained electrons or lost electrons with a +2 charge? Yeah, +2 charge. It lost them. Yes, it lost electrons. It's positively charged twice. It lost 2 electrons. So, instead of being neutral with 20 electrons, how many electrons does it have? 18. We good with that? So, the number of neutrons actually goes back to what we covered last unit. How do we get the neutrons? Yes, you subtract the protons from the 39, exactly. And so that's 19. We good with that? I think so. I'll stand here because it's cooler over here. Man, it's kind of warm over there. Okay. So is this an ion? As I have it up here? It is an anion. It's an ion, specifically it's an anion. Very good. Did it lose or pick up electrons? Picked up 1 electron. Perfect. So how many protons does this have? 17, you got it. So it picked up 1 electron. How many electrons does it have? 18. I'm liking it. So how do we get to neutrons? Yep, you subtract 17 from 36. And like I said, don't worry if you need to use a calculator for that, because I do it all the time. Okay. So we have 19 neutrons by difference. That work? I think so. Okay, so let's take a look. These will also be due, dun, 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 on Friday. Yay, Friday. Boo, homework. These look like this. Okay. So these are, for instance, they look like what we call chemical reactions, and we haven't covered chemical reactions, but this is kind of what you start with, start, then arrow, and this is what you end with. Okay, so you can kind of see that. So we're taking, in this case, a neutral magnesium atom, and we're going to get something and kick off 2 electrons. What is that something? What do you think? If you kick off 2 electrons from a magnesium atom, what do you get? What's that? You do get 10. You do get 10, but I think what we're after here, I'm going to go ahead and get you started. I'll just put an Mg, and it's going to be charged. So what do we put up in the upper right-hand corner? +2. +2, exactly. Does that make sense? So that actually is A. So A is Mg.
Like how many you get if you take away 2.
Right.
It's asking what the charge is going to be.
It's asking kind of what are you going to end with? Yeah, what the charge is going to be. Yep. What about B? Let's do that one together. Somebody said 2 electrons. Why is it 2 electrons? Because it's a +2 charge. Let's do C while we're at it. Okay, what does I stand for?
Iodine.
Iodine, yep. And here they're showing you start with iodine, and it looks like you're going to dump 1 electron on. So what are you going to end up with over here? Yep, I negative. Does that make sense? Sometimes we could put negative or -1. It's the same thing. And I'll let you do the other one yourselves. Let's pick on the next one. Let's pick on C. Okay, nitrogen. Nitrogen, we find it on the periodic table, so you need a periodic table to do this one. Nitrogen, we find it on the periodic table. I see it's atomic number 7. So, nitrogen usually has 7 protons. Well, it always has 7 protons. And if it's neutral, it'll have 7 electrons. This one has, instead of 7 electrons, it has 10 electrons. So what's the charge?
-3.
Why?
Because you're going from 7 to 10, which technically isn't adding them. You're taking, it's like the opposite with how I
You're adding them, and it makes a negative
It
charge.
makes the negative if you add 3. So instead of
Yep.
adding 3, it's not going to be +3, even just because you
Right.
added, it's going to be opposite charge.
You're adding electrons, it's becoming more negatively charged. It's lopsided. This is 7 protons and 10, bless you, electrons. So each one of those you're going to have to kind of evaluate like that. Okay? All right. But wait, there's more. Okay. These are called Lewis dot formulas. You recognize the carbon, the nitrogen, the oxygen, the fluorine, and the neon. These aren't compounds. These are, by golly, just elements. Okay. Now, if you look a little closer, I'll give you the hint. Across the top, I'm going to write what group number they are in. 4A, 5A, 6A, 7A, and 8A. And you would tell me that the group number is the number of valence electrons. Yet, so all these cute little things are doing is basically giving you the symbol of the element, and then scattered around that symbol for that element are valence electrons. That's it. That is totally it. So what this slide says is you can kind of think of the symbol as representing the center, the nucleus, and kind of those non-valence electrons. That's it. That's totally it. The slide goes on to say that, you know, it looks like you have a north, a south, or an up and a down. You have a left and a right, kind of like a west and an east. There's no significance to those. So for instance, if we pick on neon, there's no awesomeness about the top electrons that doesn't exist with the left or the right or the bottom.
Isn't there a significance in how you place them?
I think we'll see. We'll see if when we get there if you think so.
Other than maybe not more importance, but you just place them if there's 8 of them, you do 1 on each spot and then go back and do 2.
I think so. I think, but it kind of varies. If we look at carbon over here, we kind of put one we kind of scatter them around. Sometimes actually the way it works is we're going to see structures where carbon's connected to something and we're going to kind of scoot them over. They're going to kind of migrate. So it depends on what it's connected to.
Okay.
Yeah. Okay, so those are called Lewis electron dot formulas. So there's a few things that, with regard to, it's not like I disagree with your textbook, but I kind of learned it a different way, so I'll use a different term. So just be aware of that whole Lewis electron dot formula. Okay, so helium. Elements are our friend. So we find helium on the periodic table. It's atomic number 2, has 2 protons in its nucleus, and if it's neutral, has 2 electrons. There you go. That is the electron dot formula of the element helium. Sodium looks like this. Sodium is a 1A element. Sodium 1A. So don't be, bashful about looking at the periodic table. So its Lewis dot formula would look like this. Now, the other day I said that sodium, and sodium's a metal, so sodium is great at giving up an electron, right? So what the metals do is basically they give up all of their valence electrons. So sodium actually is going to kick off that one electron, okay? And it's going to look like this. Now, if we revisit, this is a sodium cation, okay? If we revisit now and look at that sodium cation, how its electron dot formula looks like. This actually is the happy sodium positively charged once cation. Sodium plus one cation. It lost that one valence electron, and you're like, dude, where did those other 8 come from? Well, what used to be just normal inner electrons now is what we call new valence shell. Put another way, and actually I've got some of these coming up. Sodium has 11 electrons, and they look like this. 1s2, 2s2, 2p6, 3s1. That is sodium. Okay? And so this guy is this guy. And when that electron goes, now what does it look like? Na plus 1, that's a cation. We have, we have 1s2, 2s2, 2p6. If I were to ask you what's the highest N, now you would say its N is equal to 2. These 8 electrons are these 8 electrons. That's it. That's totally it. Okay. Let's look at, so that's a metal. Let's look at a non-metal. Non-metals have high electronegativities. They tend to bring in electrons. Do you see how close fluorine is to having a complete octet? It only needs 1. So let's go ahead and show it picking up 1 electron. When fluorine picks up 1 electron, now it has a complete octet. And not only that, though, it's negatively charged, -1, it's an anion. That's it. I think it's easier to show how electrons are configured when they pick up electrons than to show how metals, the new electron configuration of a cation. It's a little lesson to do. Sulfur, again, non-metal, it's going to pick up, how many electrons is it going to pick up? 2. You see, just itching for those 2 electrons to get a complete octet. That's it. Okay, these will also be due. Dang, it's like bonus day. But some of those won't take very long. That one we did together, so I don't think that even counts. Okay, these are what these look like. I was looking at this morning, and I'm like, are you serious? Because what I get for each of these, when strontium, Sr, when strontium loses 2 electrons, let me put it this way. I think you can't go wrong with, when it loses 2 electrons, now it's actually going to have a complete octet. There is the first one. All of these are going to have complete octets. Is that not clever or what? Okay, to me that's the pattern for A through D. Okay, now for 34, it's a little bit different. 34 wants you to pick a noble gas. What column or what group are the noble gases? 8A, yep. So let's pick on iodine. Iodine picks up 1 electron, so find iodine on the periodic table. So it picks up 1 electron, and now it has electrons like which noble gas? Xenon, exactly. That's it. We picked on sodium. It's not up there, but let's just do this. Na plus 1. Sodium loses 1 electron, and now what's it like? It is like neon, exactly. Yeah, I think that's a pretty good place to stop. We have our work a little bit cut out for us tomorrow morning. It's kind of a normal place to be at this point in the lecture, because I need to do a little bit of background as you do your lab. It'll be fun.